Hello students, in today's class we are going to discuss on the topic of core of a section. What is the core of a section and why it is important in the case of eccentric loading that we are going to discuss today. In lot many engineering situations we encounter the components which are subjected to loading which is of eccentric nature. When we say eccentric loading, that means the load is not aligned with the centroidal axis or to the center of the object. As you can see in the figure here, there is a load of magnitude P being applied at a distance E from the x-axis. So this is the plan view here of the same component, and we can see that the point of application of load P is shifted by a distance E from the centroidal axis. So this is the amount of eccentricity that is being applied. In normal course, if this load would have been applied exactly at the centroidal axis, it would have produced only and only the compressive stresses. But because it is being applied with the eccentricity, not only it will develop the compressive stresses, it will also induce the bending stresses in this component. Why the bending stresses? Because whenever a load is being applied at a distance from the axis, so the distance is E, so the load multiplied by the distance will give the amount of moment that is being applied here. So P into E is the amount of bending moment that is being applied. So that's why there will be a bending stresses also being produced apart from the axial stresses. Let's talk first about the axial stress effect. So because of this compressive load P, a direct compressive stress of the magnitude P by A, where A is the area of cross section of this object, so that is equal to sigma A will be produced. So there will be a direct compressive stress of the magnitude load divided by area P by A, acting as if the load is acting at the centroidal axis, that will be produced. Apart from that, because as I said that the load is applied at a distance E from the centroidal axis, so there will be a couple or bending moment of M equal to P will cause the bending in the vertical plane. And we know the formula for the bending, that is sigma by y is equal to M by I. So here I have written this formula same here. So the load multiplied by the distance is P by E, P into E, so that equals to the bending moment M. I is the moment of inertia of this object about the x-axis, and y is the distance where we want to calculate the value of the stresses. So this is the amount of stress that will be produced. Now as we know that the bending stress is tensile as well as compressive. So on one part of one side of the neutral axis it is of tensile nature, on the other side of the neutral axis it will be of the compressive nature. So this load will be producing compressive stresses in this part, on the right hand side part, while it will be producing the tensile stresses at the same time on the left hand part of beyond the centroidal axis. So the total stress at any point in this object will be given by the algebraic sum of the values of the axial stress plus the bending stress. So that's why our formula for the total stress will be sigma equal to sigma A plus minus sigma B. We will substitute the value of sigma A as P by A, substitute the value of sigma B from this formula. So we are going to get this value here. Now we can calculate the value of the stresses at the extreme fibers, that means here or here, by putting the value of y equal to the depth of the section. So if you substitute that, so I by y will become equal to zx, so that will be your bending stress. So sigma max will be equal to when both of these stresses are of the same sign. So as I told you that on this part here, in this part there will be compressive stresses produced because of the application of the load, plus there will be compressive stresses because of the bending effect. So both of them will add together, so there will be a positive sign here between sigma A plus sigma B for this the stresses in this area, while from the other part there will be tensile stresses, so there will be sigma A minus sigma B component that will be acting there on that part. Now if I draw the value of stresses at the section if I find that sigma A is greater than sigma B in magnitude, that means the compressive stresses magnitude are greater than the bending stress value. So they will add on the right hand side part. So sigma A and sigma B, they both are of compressive nature, so they will simply add together. On the left hand side, because they are of different nature, so sigma A minus sigma B will be the value of the remaining stresses. So this is a kind of a shape that you are going to get for the stress distribution along the cross section for the eccentric loading case. Now if the sigma A and sigma B value both are equal, so in that case there simply will be twice of the sigma A or twice of the sigma B on this right hand side portion, while on the left hand side they will subtract from each other and give you the value as 0. So our neutral axis in this case will shift to the extreme end of the fiber here. Now if sigma A is less than sigma B or sigma B is greater than sigma A, in that case here of course they will add together sigma A and sigma B value, but on the other side the value will remain of the tensile nature and its magnitude will be given by sigma B minus sigma A. So that is the value of stresses that you will obtain here. So on one side of the component you are getting a compressive stress, on the other side of the component you are getting a tensile stress. In the upper to these two cases that we have considered, sigma A greater than sigma B or sigma A equal to sigma B, there will not be any tensile stresses present in the section. So we see if the bending stresses are higher in magnitude in comparison to the axial stresses, there will be tensile stress produced in the section. As the bending stress depend upon the amount of load as well as the eccentricity also. So for the given load, it is the eccentricity value E that will decide how much is the bending stress produced. So if the E is high or large, the sigma B value will be high also, and it can become more than sigma A, causing the tensile stress to get produced in the section. Now this information is very important for the simple reason that in the masonry or the concrete structure which we usually encounter in the civil engineering, we find that these structures can take lot of amount of compressive stress. So concrete can withstand very high amount of compressive stresses. But as when we go about and talk about the tensile stresses, the value of permissible tensile stress for concrete is not so much as compared to compressive stresses. So there should not be any tensile stresses. The production of tensile stress may cause the cracks to develop into the concrete. So that's why when we are designing these components, we need to see that the load that are coming on these masonry structure, let's say the columns or the pillars that we give in the civil engineering structure, they should not have the eccentricity value so high that will cause the bending stress to be produced more than axial stress, causing the tensile stress to be present in the section. Because as we know that these structures are good enough in the compressive stress but not so good in the tensile stresses, and they will break away in that case. So that's why we need to limit the value of that eccentricity. Now we know that sigma A should be greater than or equal to sigma B in order that the stress sign does not change. That means if I say P by A should be greater than or equal to M by Z. If I substitute the value of bending moment M as P into E and the value of Z as I by D by 2, where D is the depth of the section, so this is going to give me the PED divided by 2I, this value here. So if I, instead of I substitute area of cross section multiplied by the radius of gyration square, AK square, then I can cut this P and P from each other, and A can be cut from each other. So what is left is E should be less than or equal to 2K square by D. So that gives us, this formula gives us the limiting value of the eccentricity, which tells us that if the E value is less than or equal to 2K square by D, we are not going to get the tensile stress produced in the section. If E is larger than this value of 2K square by D, obviously there will be tensile stresses produced, which can be detrimental for, let's say, the concrete columns or the structures. Now let's find out that how this formula will work for the different kind of section. Let's start with the rectangular section. So for the rectangular section, the value of I is given by BD cube by 12. This is what we are familiar with. And the area of cross section of the rectangular section will be simply width multiplied by the distance, B into D. depth of the section. So that gives us, if I substitute for I and A these values, this give me the value of k square as d square by 12. If I use the equation 1 and 2 together, this will give me the value of eccentricity as should be less than equal to d by 6. So you see, for a rectangular section, if I have the eccentricity on the depth side, which is less than 6 on one side of the centroidal axis, I'm not going to get the tensile stress produced in this. Similarly, to the other side of the centroidal axis also, we are allowed to move up to the distance d by 6. So that means we at the all together on this variation of the eccentricity point can occur by d by 6 plus d by 6, that is d by 3. So 1/3 of the distance we can move along the center for the case when we don't want any tensile stress to be produced. So that's why this is called as middle third rule. So from the middle third area is distance is safe for the point of application of load to move, so that your value of stresses will not become negative in nature. So that's what I am stressing here, that the stress will be of the same sign throughout the section if the load line is within the middle third of the section. D by 6 plus d by 6, that gives us d by 3. Now the maximum stresses that we can occur at the extreme fiber will be that we can calculate by substituting the value of area and section modulus Z here. So I have substituted for the area as B into D, and for the section modulus I have substituted BD square by 6. That is the for the extreme fiber case. So that gives me the maximum stresses that were produced as P by BD into 1 plus minus 6 into E by dVd. Now at the moment what we have considered, that we are moving the load point only along the axis YY. Okay, this is the another centroidal axis. X-axis is one of the centroidal axis, YY is the another centroidal axis. So if you have the arbitrarily, if you want to see that at any point along the section how much I can move the load, or how much I can move the load away from the centroidal point or centroidal axis. So this is what we are going to calculate in this core of a section. So there is a certain area where the application of load or force P will not yield in tensile stress. Such area is known as kernel or the core of the section. So let's find out the core of a section for a rectangular section. So what is given here is a rectangular section which is having width B and depth D, and these two axes which are the centroidal axis here, XX and YY, about the width and the depth. So I have shown it here. Let's take a point P which is, let's say, located in the first quadrant. So we have this coordinate of this point as given by X and Y. So we know the coordinate of this point. It may be, let's say, D by 2 or B by 2 or D by 3 or B by 2 and whatever point, but it is a positive points on both X and Y axis. So it is in the first quadrant. So we are considering that the application of load is anywhere at any point in a first quadrant. So we want to calculate the stress at the other points in the section. So the stress at any point having coordinate x dash, y dash in general will be given by the equation which I have written here. So this stress will be sum of, number 1, the axial compressive stress, which is due to the application of load P, so which will be simply load divided by the cross section area of this section. So because it is a rectangular section, so cross section area will be B into D. So P divided by BD will be the amount of compressive stresses that will be produced. Now the second type of stress that is being produced because of this load, because load is not acting exactly at the centroidal point of the cross, exactly at the origin point. So that's why it is at a distance of y from the x-axis and at a distance x from the y-axis. So it is eccentric both in comparison to x-axis and y-axis. So it will generate two type of bending stresses, one about the x-axis, another about the y-axis. So one bending moment will be P into x, another bending moment will be P into y. So for the first case we are talking about the x-axis because it is acting, the load is acting at a distance y from the x-axis. So the bending moment value will be P into y. The value of the moment of inertia about the x-axis in this case will be 1 by 12 dB cube. so which I have written here. Now the distance of the extreme fiber in this case, because I am trying to calculate the value of stresses at the point x dash and y dash, which is anywhere in this rectangular section, so I am going to substitute for value as y dash here. Now the second part, because this load is at a distance of x from the y axis, it will produce the bending stress about the y axis also. So this will be, the bending moment will be p into x. The value of our moment of inertia about y axis will be 1 by 12 bd cube, and the distance of the point and where we want to calculate the value of stresses is x dash from this axis, so we will put here x dash. So you see there is a one component of compressive stress and the two components of bending stresses which we need to add together in order to obtain the value of stresses at the point x dash y dash. Now let's see this figure also. Okay, now if I bring out the common values of 12p by bd, I am going to get an equation which is shown over here like this. Now let's define this point x dash y dash where we want to calculate the value of stresses. Let's say that we want to calculate the stresses at extreme point D here, which is in the third quadrant. So we want to calculate the value of stresses at point D. So the coordinate of the point D is, because we know that the width of the section is dB and the depth is d, which is shown here. So the coordinate of this point D will be x dash equal to minus d by 2 and y dash equal to minus b by 2, because it is in the third quadrant. So thereby, that's why there is a negative values here appearing in front of the d by 2 and b by 2. When we substitute these values in equation here, we are going to get the value of sigma as 6p divided by bd multiplied by 1 by 6 minus y by b minus x by d. Now we don't want this value to become tensile in nature, so at the most it can go to become 0. So that's why we'll substitute this value sigma equal to 0. So this will give me equation which is shown over here, y by b plus x by d equal to 1 by 6, which we can simplify as equation A, which is shown below. Now this is the equation of a straight line. You can see this 6y by x plus 6x by d equal to 1 is the equation of a straight line, and this gives the deviation of load, how much the load can move, and load can move along this straight line, and we are not going to get the tensile stress if the load is within this range. So this line equation, if you substitute x equal to 0, it will give you the value of y equal to b by 6. If you substitute y equal to 0, it will give you the value x equal to d by 6. So it will intercept with the line at d by 6 and y equal to b by 6. So where will this lie? This line is going to be this line here. So this will be at value of y equal to this x equal to b by 3, d by 3, and y equal to x equal to d by 6 and y equal to b by 6. These are the coordinates of these 2 points here, and so this is the line we are talking. We have just obtained the equation of the line hj, right? So if the load is moving beyond this point, okay, that means towards the center, then we are not going to get the compressive stresses. If the load goes beyond this point, anywhere in the first quadrant, we are going to get the tensile stresses at the point D, okay, which we don't want to occur. Now as I have just done the calculation for the first quadrant, keeping the point in the first quadrant and taking the point of stress calculation in the third quadrant, I can do the similar exercise for the other quadrants also. If I do this exercise there, I am going to get the equations for the second quadrant, third quadrant, and fourth quadrant also. They all equations will turn out to be straight line. So at one point I am going to get the equation for GH. Similarly, I will obtain the equation for GK, and then finally for the KJ. So that's why this is going to give me this rhombus. And what these equations are going to tell me, that if the load is moving anywhere in this rhombus area, I am not going to get the tensile stress anywhere in the section. If the load goes beyond these beyond this rhombus, if the load is, let's say, here or here or here or here, at any point I am going to get the tensile stresses produced, which I don't want. So this rhombus area where the load can move around without getting the stress values to be tensile anywhere in the section is called as the core of a section. That is what I have defined here. So system will be wholly compressive if the line of action fall through the rhombus GHJK. This rhombus is called the core of rectangular section. Okay. As we have done the calculation for the rectangular section, similarly we can do the exercise for the circular section also. In this figure you can see a circle is a cross section is given which is of diameter d, and we know that the formula for calculating the eccentricity, limiting value of the eccentricity, is 2k square by d. Now for the solid circular section, the moment of inertia value I is given by pi d4 by 64, that we know already, and the area of cross section of the circular section will be pi d square by 4. If you substitute these two values here, you are going to get the value of radius of gyration as d square by 16. And when we use it in the formula of eccentricity, limiting eccentricity formula, it is going to give me the value of eccentricity should be less than equal to d by 8. So that means from the center I can go move extreme distance of d by 8 only, as I can move on the both side of the center by distance d by 8. So that means the total circular area that I am allowed to move around the center is d by 4. So this is what is shown in this figure here, and you can see here that this is the core of a section. So that is d by 4, 1/4 of the diameter value of the circular section. Because it is 1/4 of the diameter value of the circular section, which is safe to move around without getting the stresses to become tensile in nature, so this is called as the middle fourth rule. So with this middle fourth area, if you move around in a circular section, the stress values are always going to remain compressive in nature. The tensile stresses will not arise in this case. As we have just done the calculation for the circular section, let's quickly do the calculation for the hollow circular section also. So here we have a hollow circular section whose external diameter is capital D, internal diameter is small d, and we know that for the hollow circular section the moment of inertia value is given by pi by 64, d outer diameter to the power 4 minus d inner diameter to the power 4. The area of cross section of this hollow circular section will be pi by 4 d square minus small d square. If you use the value of these moment of inertia and cross section area to calculate the value of radius of gyration k square, you are going to get the value of k square as d square plus small d square divided by 16. Now let's use the formula for limiting value of the eccentricity, that is 2k square by d. And mind it, here the d is called the depth of the section, as the maximum depth of the section here is equal to the outer diameter of this hollow circular section, which is represented by value of capital D. So for the value of depth here, this d, I am going to substitute capital D here. For the value of k square, I will substitute d square plus d square small d square by 16. So that's why it will give me the value of limiting value of eccentricity as equal to less than equal to d square plus d square by 8d. Now this is the value of eccentricity around one side of the center. So the exact distance I can move around the center will be twice of it. So my core of the hollow circular section will be a concentric circle of the diameter capital D square plus small d square divided by 4d, which is shown in this figure by this shaded area. Now this brings us to the end of this discussion today, and we see that we can calculate the core of the section. In fact, in our university itself, in the building, that if you come when the this COVID situation will permit us, you can see that there are some columns of concrete which are circular columns. They have been increased in their diameter. The simple reason is to increase the diameter is to move their point of eccentricity within the core of a section. Earlier, these uh, concrete pillars were developing cracks on its edges, and the simple reason was that the load is being applied eccentrically, and which was causing the tensile stresses to produce. As the concrete could not withstand the tensile stresses, there were cracks which were appearing there. So there was a treatment which was carried out. So there was some drilling which was carried out at the outer periphery, and then these thickness of the diameter of these columns were increased, and now you can see that there are certain columns, circular columns, which are much larger in diameter in comparison to the other columns which are there. And this work was carried out, this maintenance work was carried out, and by that we were able to suppress the tensile stresses production or the cracks production in these columns. You can see some other examples also. I would suggest you to look around yourself and see where you can find such eccentric loading in the machine components.